Hello everyone, today I'm going to present to you paper 1 of Nanyang Junior College 2019 prelim paper. So I'm going to share with you the strategy and tips to solve the MCQ questions. So there are a total of 4 papers in the A-level chemistry, 9729 version, that is a Singapore Cambridge version. So for paper 1, we have a total of 30 questions in the current syllabus. Now, so the range of topic is all the way from atomic structure to the last topic, organic chem, which is nitrogen compounds. So this is the first question on atomic structure. So in this model, the nucleons can be further divided into more basic particles called quarks. So quarks are particles that occupy spaces and also have charges with some positive and negative charges. So these are the subatomic particles in quarks. Okay, we have the up quarks represented by U plus 2/3 as the size and the polarity. Down quarks represented by D minus 1/3, electron minus 1, and neutrino Be 0. So in a radioactive reaction, this process occurs in the nucleus of the atom. So nucleon A break down to nucleon B and C and VE. So VE, so let us see how do we approach this question. So what you can do is you can write down the charge and the magnitude of this first. So this one is 0. There's no size, no polarity for this. Okay. Now, U represent plus 2/3. So you have plus 2/3 here. D, minus 1/3. Correct? D minus 1/3. So if you add up together, you have so the charge of this is neutral because 2/3 minus 1/3 minus 1/3 equals 0. Okay, so this one has no charge, so it's just a neutron because neutron has no charge, ma. Okay. So it's a neutron because no charge. As for nucleon B, we have plus 2/3 plus 2/3 minus 1/3. Okay, so add up together, you have plus 1. So you have a plus 1, so this must be a proton. Okay, it has a plus 1 charge. So if this is plus 1, this is no charge, then what is particle C? Particle C can only be minus 1. All right, because you need to balance the charges. Plus 1 minus 1 gives you 0. So the charge on nucleon B is plus 1. That's correct because we have already calculated that. Okay. Particle C is deflected towards the positive plate. Yes, because this is negative, it will be deflected to the positive plate. So particle C will move towards the positive plate because opposite charge attracts. The process is described by Ne22 become Na22. So you can see that if this is true, then do you notice that, okay, neon, okay, the neon is just before sodium, right? So so from neon becomes sodium. You see the neutron become a proton, but the mass number is still 22. So this means that the proton number increased by 1. So it is true. Since sodium is above neon by 1. So neon is 10, this is 11, right? So you can see that here the change, the difference will give you the number of neutrons, give you 12. This one will give you 11. So when one of the neutrons become a proton, it will be 11, become 12. So the sodium, the particle gain 1 more proton to become a new element, sodium. Okay, so this is correct also. So answer is A. Okay. because from neon to sodium, there is a +1 positive proton number, correct? Proton is positive charge, so there's 1 plus proton. So one more proton, but 1 less neutrons, all right? Since the mass number is kept constant. So in that case, in order to maintain this, the neutron here is 10, drop to 10. Then this one drop to 11. Yeah. All right. Okay. Drop to 11, sorry, not 10, 11, because after you minus away this, you get. So the new particle has 11 proton, 11 neutrons. The old one has 10 protons, 12 neutrons. So one go to here, become 11. This one drop to 11. Okay. Number 2. An oxygen candle provides emergency supply of oxygen. So there is sodium chlorate in the mixture. When ignited, it burns at this temperature. At this temperature, there is decomposition, releasing oxygen gas and sodium chloride as the only product. So these are the number of moles of oxygen and number of moles of sodium chloride. Okay, now let's write the formula. So basically it's something like Na. Okay, let's ignore the spectator ions here. So we make it easier. ClOx. Because we do not know what is it. So the oxidation number of chlorine will affect this thing. So you form oxygen gas as Cl minus. Okay, since they said that the number of moles is 0.1 here, 0.15 mole for oxygen. Okay, the mole ratio is, so Cl minus to O2, 1.5 times 2, 2, 3. So the mole ratio is 2:3. All right. So you have 3 mole, 2 mole. Okay. All right. And we know that oxygen in alkaline is peroxide, right? Okay. Normally the oxidation state of oxygen is -2. Okay. So we can see that for oxygen alone, right, from -2, oxidation state here becomes 0. Okay. How many electrons are involved? So you see that 3 oxygen molecule. Okay, so the total number of electron loss. So oxygen is being oxidized, so electrons are lost because you are increasing the oxidation state from -2 to 0. So the number of electron lost by 3 oxygen molecules. For 1 mole of this is 3 mole. All right, so we will have 3 times, because it's 2, so 2 times another 2 because O2 ma. So you have 12 mole of electrons, 12 number of electron transfer. If you look at chlorine, it gains, so the number of electron lost by oxygen will be equal to number of moles of electron gained by chlorine. Same. So by the 2 chlorine, the 2 chloride ion, right, is also 12. By right, it should be 12. Because the number of moles of electron transfer should be the same. Number of moles of electron gained by oxygen should be equal to number of moles lost by oxygen should be gained by chlorine. The number should be equal. The electron transfer number. So how many electrons lost here will be equal to number of electrons gained by chloride. Okay. So in that case, but there are 2. So number of electrons gained by each chloride. Each chloride will gain 6. So 6 electrons are involved. So the change in OS of chloride is 6. So final oxidation state minus initial is -6. -6 because the final is more negative than the initial. Okay. So the final oxidation state is the is -1 here for each chloride, -1 ma. So initial oxidation is the one that you need to find ma. So -6. So the initial oxidation state will be equal to -1 plus 6 will be +5. So answer is B. So it is NaClO. It is +5 here. Then here will be -3. So it's NaClO3. That's the formula. So if they ask for formula, this will be this +5 minus balance it. Okay. Okay, number 3. Cations with a high charge density can polarize adjacent anions. This results in ionic bonds with covalent character. However, if the oxidation state is high enough, a covalent bond will form instead. So which leaves the most ionic and most covalent halide compound? So to have high charge density, okay, so what is charge density? Is charge over the radius. So the higher the charge, the higher the charge density. The smaller the radius, the higher the charge density. So we expect the cation to have high charge and small ionic radius. Okay, it's ionic radius, not covalent radius. Okay, so this cation with high charge density will then be able to polarize the anion electron cloud more to form the covalent bond. Okay, so for ionic compound, our group, okay, all these are, they are comparing between 14. Okay, tin and lead are in the same group, group 14. All right, so we look out for cation with a smaller 2+ charge. So obviously, the most ionic one will be the one that has a small charge and a large radius. Whereas the most covalent one will have a high charge and small radius. Okay, it's because the one with a higher charge density will most likely form covalent halide compounds, whereas the most ionic one will have small charge and large radius. So to have a small charge, it must form the +2 instead of +4. So here you can see that the ion charge is +4 for the cation. The cation here is +2. So it's between A and B. Okay, then compare between tin and lead. Okay, between tin and lead, right, we know that down the group, since they're in the same group, down the group, the radius will increase. Okay, so to have large radius means lead is below tin in the group. So lead ion should have a larger radius because it's below tin in the same group. Okay, so it will be B. Okay, so for covalent compound, to confirm whether it's B, we check whether it works for this. So for covalent compound, look out for high charge and small radius, so it will be tin, and it has a smaller radius than this, so it will be B. Okay, it's good that you know that anions with larger electron club will be more easily polarized. Chlorine, for example, is actually more easily polarized because it has a larger electron club size. So it will be able to form covalent bond more easily than fluorine. Okay, let's go to number 4. Okay, number 4, they're asking for which bond angle is not present in the molecule of compound Z. Okay, so let's examine each angle. Okay, now to see if any of these fall under this, then it will not be the answer. All right, so let's check out for this one. Okay, so this one is the angle of this, right, will be around, because there is there's bond pair, lone pair repulsion. Okay, so this one, because of the repulsion here, it will be greater than 90 degrees. Okay, so it will not be 90 degrees. Okay, so this one will be, there will be some repulsion. So this will be actually 120, around there. Okay, therefore, we all know that for carbon in the benzene ring, right, okay, is always 120. Okay, between these two bonded lines. So this is out. As for this one, right, there is some repulsion, so it's not exactly 180. In fact, because of repulsion between bond pair, it's around 180. Okay, then for this one, right, is around 180. So this is out. And for this one is around 105. So this one 120, no need to say. Okay. So the only answer, right, would be also 105 also out. Yeah. Will be 109. How to get 109? What is the shortcut to this? As you can see in the structure, right, there is no sp3 hybridized carbon atom at all. Look carefully. There is no sp3 hybridized carbon. So to have sp3 hybridized carbon, right, there is no 4 bond pair with 0 lone pair. No. Only this arrangement, right, 4 bond pair with no 0 bond pair, will give an angle of 109 degrees. That will give you 109 degrees bond angle. But we don't see that. All right. At all. Okay, we don't see that at all. So it will be 109 degrees long, because there's no sp3 hybridized carbon atom. Okay. Now, the next question is on ideal gas. So you have a mass of 0.253 grams of volatile liquid injected into a gas stream at 97 degrees Celsius. Initially, before the injection, it was 5 cm3. So before anything was inserted, it was 5 already. After the vaporization, it became 81. So you be careful. 25 cm3 is due to the air particles already present. So the actual volume of the volatile liquid that vaporizes, right? The actual volume of the volatile liquid, right? That vaporized, right? Should be 81 minus 5, which is only 76 cm3. Okay? Now, then you plug in the formula PV nRT. Okay, MR is a subject, so you convert this to mass over MR. Okay, later take note of the units. So put MR on this side to make the subject of formula nRT/PV. Okay, the mass, okay, is given at 0.253. You can just use that because the number of moles is derived based on grams. So don't change this. Don't change the mass in grams. R you derive from data booklet 8.31. Temperature you have to convert to Kelvin. So plus 273 to 97 degrees Celsius. The pressure, okay, the pressure is given as atmospheric pressure. So this one need to convert to SI unit, Pascal, which is 101,325. Be careful, it's not 1.01 only, it's 101,325. Must copy down everything. Then for the volume, be careful. Here is in cm cube, right? You have to convert to meter cube. So you need to times 10 to the power -6. Divide by 1000 to get dm cube, and divide by 1000 to get a meter cube. So this one must be in meter cube, SI unit. This one no need, this one yes. The rest yes. And then you just punch in your calculator, you get around 101 B. Okay? The next question, for the energy cycle given below, which enthalpy change is correctly stated? So this question tests on how well you know the definitions of the different enthalpy, and you need to refer to the data booklet to find some values, okay? Now, so look at statement 1. It says that delta, this one, delta 7, right? Delta enthalpy change is 7. Is equals to 8 minus hydration of calcium minus hydration of Ca 2 plus and minus like that only. Okay. Okay, as you can see, delta enthalpy change of 7, right? Is actually telling you what? Lattice energy. Of calcium carbonate. Can you see that? Lattice energy is energy released when gaseous ions, okay, form the ionic product. One more ionic product. Okay. And this one, 8, is definitely solution. Equals to solid, it's a reverse of solution. So it's negative solution calcium carbonate. Okay, since I want to know about hydration, let's verify this. And we know that, okay, enthalpy change of solution is equals to total or sum of hydration minus lattice energy. So this is the definition. Okay, we take hydration minus away lattice. Okay, the reverse, and then we hydrated the ions to become equals, then it will give us the solution. Okay, so this is the definition. So lattice energy is the same as like this. Hydration minus solution. Okay, so hydration isn't it this? So this is hydration, no? Plus. So lattice energy is calculated by hydration of Ca2 plus hydration of CO3 2 minus. So it should be this hydration, the two hydration add together minus away this, and not this is wrong. Yeah. So this is out. And for statement 2, you need the data booklet. Statement 2 says this one is equal to 1740. Let's check. This is ionization energy. Ca plus E minus. Ca plus, the second IE, 2 plus E minus. So you find the IE of calcium. The first one is 590, the second one is 1150. Add together 1740. It's correct, kilojoule per mole. So statement 2 is correct. Statement 3, okay, you have to use the Hessen's law. They say that enthalpy change or atomization of calcium Okay, where is calcium? Which is here. This is atomization. Okay, let me erase this first. Okay, so this is calcium. This is atomization. The definition from solid becoming gas. This is enthalpy change or atomization. Okay, 1 mole of gaseous element atom from its reactant from the elemental state. Okay. So to get this, to find this, right? Let's determine this to see whether this makes sense. Because of H1 here, right? We do our own one. So H1, okay, work backward lah. So it's equals to H2 plus H3 plus H4, correct? Plus H5 plus H6 plus H7, but here is the opposite, so become minus H8. If you reshuffle the equation, or rearrange rather, to make H2 the subject, you have H1 plus H8 minus H3 minus H4 minus H5 minus H6. Luckily, everything is in one, so easily. Doing that, then you check the given. It's the same. So this is correct. So 2 and 3 is correct, C. Okay? Okay, number 7. The setup is shown to determine enthalpy change of reaction for neutralization of oxalate acid, H2C2O4, using a calibration method. So you're supposed to find out this one, the enthalpy change of solution. So in the first experiment where they actually use HCl, but what is the same between them is you need to understand that the specific heat is the same because they are using the same setup. Okay, so the specific heat is the same. All right. So what is different is the chemical use lah. All right. So and we need to understand that, okay, the total amount of heat evolved depends on how much water formed, because this is on enthalpy change of neutralization. So it depends on the number of moles of water. Okay. So for the first experiment, right, there is no limiting reagent. It's the exact amount for each reactant. All right. So you just take any one of them, it's fine. So the number of moles of water for the first experiment will be 2 times 50 over 1000. Convert the 50 cm to dm3. Okay, so this is the number of moles of water. So leave it like that because in the choices, right, they did not convert it to final answer lah. All right. So using heat evolved, so amount of heat evolved, okay, is equal to the heat absorbed. Okay. So the heat evolved is equals to, since they give you 57.4, they give you an enthalpy of neutralization for the first experiment. So you just take the number of moles of water times this one, give you the amount of energy, ma. Correct? The heat absorbed is MC delta T, ma. How much energy absorbed by the water? So amount of energy released equals to energy absorbed. So the heat capacity is C times temperature rise 10. So the heat absorbed by the solution. Okay, heat evolved by the reaction is absorbed by the surrounding. The solution is surrounding, they absorb the heat. Okay, so you form equation 1 here. Then look at equation 2. This time around, be careful, there's a limiting reagent. Okay, so you can see that from the equation, we need 2 more of sodium hydroxide, right? So confirm this is the limiting. Because the mole ratio show 2:1. Okay, but we only have this amount. So we use sodium hydroxide instead to calculate the number of moles of water. So because sodium hydroxide is the limiting, so the number of moles of 1 mole of the enthalpy change of neutralization for the second experiment will be because it's 2:2, so we base on this. So number of moles of or C2 or H2 C2O4 reacted, okay, is equals to 2 times 50/1000 times. So the number of moles of acid that reacted is only half of it. Okay, only half of it. Okay, so because this is the excess, this is a limiting, right? Correct, sorry. So as NaO is a limiting, so the number of moles of H2C2O4 reactor is half of this actually. So this is actually how much that really reacted. Yeah. With that, right, you equate this to this one, heat evolved equal to heat absorbed, right? So you have 2 times 50/1000 times half times, so this is the number of moles, okay? Times the enthalpy change of solution, which is the unknown in the finding, equal to C times 8.5. So this will form equation 2, okay? Okay, after which, you take equation 1 or equation 2, divide by equation 1. Solve it mathematically. So equation 2 is 2 times 50/1000. All this is math already. Times. So we can cancel off the heat capacity, which can cancel each other later. Then this one is 2 times 50/1000 times 57.4 equal C times 8.5 C times 10. Okay? The difference in temperature, no need to convert to Kelvin, no need. Now cancel. Cancel. This one move over. Then you will have to bring over become 2 times 8.5. Now move over times 57.4 divided by 10. You look like A. Okay? Take a look at this question again before we move on to the next one. Okay. With that, we move on to question 8. For question 8, right, they're asking which process show different sign of delta G and delta S. So I have to do it individually. So you have to understand when, for example, silicon chloride to water, what is formed. So when silicon chloride, you must write the state symbol for clarity. Okay, so we added the water. So silicon chloride is actually liquid. Okay, so when added the water, it forms silicon dioxide solid plus 4HCl. Okay, so in this case, right, you can see that, okay, for delta G, right, to be, will this reaction be like most likely to form? Answer is yes. Okay, this reaction can occur quite easily. So delta G is negative. Delta negative means likely to favorable to form, so likely to happen. But for delta S, for this one, delta S, right, in this case, is liquid. You have 3 liquid becoming a solid. So you are the entropy 3, but you have forming 4. So it is more disordered because you are forming more equals, right? Yeah, so it is positive. So they are different sign. Okay, so different sign, you have to give a tick because it's more entropy, because more equals. Then look at 2. So for this one, bubbling chlorine gas to iodide. For this one, right, it's obviously delta G is negative, confirm negative, because most likely to happen, very easily happen because chlorine is more reactive than iodide. But for delta S, right, it's also from gas become aqueous. So gas become aqueous is actually more orderly, right? Yeah. So it's actually negative, same sign, so cannot. Because it doesn't become more disordered, it become more ordered. Because from gas become aqueous, yeah. Then for the last one, magnesium carbonate decomposes. So you have solid, then you have a gas. So the entropy wise obviously is positive, become more disordered. Solid to gas, opposite of this one. But this reaction not likely to happen so easily. So it is positive. Negative means get free energy, negative means likely to happen. So this is out also. So the same sign cannot, so it's only D. Okay, next, number 9, kinetics. So for this question, right, they already said that this is a reaction. Okay, let us see. So what can be deduced? So the first statement says that, okay, it is first order. Let's check. Okay, with respect to Cl2. So graph of color intensity against time show first order characteristics with constant half-life. Can you see that it's constant half-life? So half. So it takes the same. Half-life means time taken for half of it to drop, right? Yeah. Another half is, half of half is 1/4. So it dropped to 3/4. Okay, so the half-life is quite consistent. You can see that the constant half-life. Yeah, 1/4, then 3/4. Okay. So given a constant half-life, right, it is first order. Since NO is used in excess, right, the variable should be Cl2. Because, so it should be Cl2, the variable. So as reaction progresses, the rate decreases proportionally with decreasing Cl2. So it must be first order with respect to Cl2. And also, this is a supporting graph to prove that it's first order. The graph of rate against NO2 square shows a straight line with constant positive gradient passing through the origin. So the rate is directly proportional to NO to the power of 2. So we can tell that this is, so means that with respect to NO, right, the order of reaction is 2. Okay, statement 2 tests whether you can draw the link between order of reaction and the stoichiometric coefficient in the mechanism. So since it's first order with respect to Cl2 and second order with respect to NO, right, it tells us that one molecule of Cl2 and 2 molecule of NO take part in the reaction, up to and including the slow step of the reaction. For the given mechanism, right, where the slow step is the second step, the mechanism will be consistent with the rate equation. So you can see that for statement 2, is it 2 molecules NO? Yes, if you combine the equation, yes, it's 2 molecules of NO. So it will be NO2 plus Cl2. If you combine these two, this one cancel off. So it's 2, 1. The second step should be the slow step. Okay, so this mechanism is consistent with the rate equation. Nothing wrong. So this is correct. Statement 3, what is the rate constant? So overall, you have NO to the power of 2, Cl2 power of 1. So it is a, overall it's a third order reaction. So for third order reaction, right, the rate constant should be, okay, the rate is mole dm cube per minute, correct? Since we have 3 concentration, right, so it should be like that. Power of 2. So you multiply them together, you have mole 3 dm cube minus 3 minus 6 give you minus 3 minus 6 minus 9. That will give you mole minus 2 dm 6, 9 minus 3, 9. So this should be the correct rate constant because overall order is 3. So it looks a bit weird, right? So it cannot be this one. So it's only 1 and 2. Okay. All right. Let's go on to number 10. So this is on the decomposition of hydrogen peroxide. It's a first order. We did say first order. So if 10% of hydrogen peroxide in the solution of concentration 0.1 decompose in 5 minutes at certain temperature, what is the concentration of 1 mole per dm cube after 5 minutes at the same temperature? Okay. So since it's a first order reaction, the rate is directly proportional to the concentration of H2O2. So the time taken to use up 10% of initial amount remain constant. So after 5 minutes, right, we'll expect to have 90% of the initial H2O2 remains. Because 10% decomposes, so 90% will remain after 5 minutes. Okay, so to prove the rate is equals to K times H2O2 concentration, right? We prove So when concentration of H2O2 is 0.10 mole, okay, the rate will be equals to 0.1 K. Okay, 10% of 0.1 K is 0.01. So at the rate of 0.1 K, okay, it will take 5 minutes to use up 0.01 mole per dm cube. Okay, so at the rate of 0.1 K, it will take 5 minutes to use up 0.01 mole per dm cube H2O2. When H2O2 is equivalent to 1 mole per dm cube, okay, the rate is equals to K times 10% of 1.0 mole, okay, which is 0.10 mole per dm cube. So when the amount to be used are increased by 10x, and the rate also increased by 10x, the increase cancel out and the time taken will still remain at 5 minutes. So for this case, right, it doesn't matter. Okay, as long as it's the first order, all right, same temperature, the concentration, right, will still be another 10%. So it should be D. Okay. Okay, let's move on. 11. The pH of human blood is constant about 7.4. What ion is present in human body will remove contaminated H+ from the blood to keep the pH constant? Okay, so this is based on whether you remember what is in the blood. So human blood is buffered by this. Okay, so the weak base will react with and remove some amount of H+ to keep the pH around 7.4. So this is the equation that help to balance the pH. So it will be B. It's based on remembrance. Okay, recall. Okay. I will continue with part 2 the next time from question 12 onwards. So that's it for today for my part 1 series. Thank you.